Hey everyone, welcome back to Quick Soil Mechanics Lessons with Brian. We will continue with lessons in pore pressure. In this video, lesson number 5, case history. Just to review, the effective stress is total stress minus pore pressure. So understanding pore pressure is incredibly important, especially to slope stability of a dam or embankment tailings facility. So let's look at this case history. We have a center line constructed tailings facility. See the embankment on the right-hand side, tailings on the left, water pool on top. And it's quite a tall tailings facility. And at the base, we have a single vibrating wire piezometer. And that was installed at about the natural ground. So it showed a very low core pressure in there. And there was also some CPT attempts, but it was refused less than halfway through the deposit. So the designer presumed that this is the phreatic surface, reflecting the pore pressure in that vibrating wire piezometer. But and that resulted in obviously a low phreatic surface and a high factor of safety. But I wasn't buying that, so I asked for CPTs to be completed with drilling. So CPT down, drill that out, CPT down, drill them out, and run multiple pore pressure dissipation tests through this exercise so that you can get all the way through the facility. So where this was the previous interpretation with the one vibrating wire piezometer that was installed at the ground surface, now we've got all these dissipation tests all the way up and down. So this is obviously not the low phreatic surface that was interpreted there. And it looks a lot more complex. So if we drew a single phreatic surface through there, we might think that it looks like this because of that uppermost pore pressure. Well, that is not the case. And if we remember a previous graphic from Charles Ladd's 22nd Earl Terzaghi lectures called Stability Evaluation During Stage Construction, excuse me. It's a really brilliant paper, and if you haven't read it, you need to read it. And I would say read it 3 or 4 times. It takes that much to understand the content. It's a really good paper. So in this paper, we investigated an upstream constructed tailings facility, and they were looking at the slope stability and what's labeled as slimes here, which is the finer fraction, the siltier fraction of the tailings. You can see this kind of elongated bullseye target. So the word slimes is surrounded by contour lines that say 40, and then it goes down to 30 outside of that target zone, and then you can see it 20. So this is exactly like a bullseye, elongated bullseye. And what that is the pore pressure. So the pore pressure is highest in the middle of that deposit and lowest at the base and lowest at the top. So this is like uh, a odometer test that's got drainage at the top and bottom. And you can see off to the right-hand side below the starter dam says sand and gravel. So there's drainage going into the sands and gravels, so we don't have a normal hydrostatic condition. We don't go down 1 meter and we have 1 meter of head. We have increasing toward the middle and decreasing toward the bottom. So that's a lot like that odometer that's the drainage going on. So if we look at this again with this phreatic surface drawn in here, that phreatic surface is just utter nonsense, as was that very low phreatic surface. And instead what we have is a very complicated, elongated bullseye coming through here. So we've got same thing. We've got drainage into the natural ground, atmospheric at the top, and non-waste in the middle. So it's draining through the bottom. And if we had one and only one piezometer in here, we would have absolutely no idea what the pore pressure regime is in here. So I've been for a long time an advocate of installing multiple piezometers. In this case, it was pore pressure dissipation test, which is of course just a snapshot in time, but it's not going to change that much over the shorter durations. So this could be used in the slope stability analysis. So you can see we've got the highest pore pressure in the middle, lowest at the top and bottom, atmospheric at the very top, and possibly close to atmospheric at the bottom if it's draining well into a free draining base. So now, doesn't that look just like the figure from the Kurzweil lecture? Yeah, it looks a lot like it. And now we've got a realistic pore pressure regime, and we can run our slope stability analysis on this thing where you can see the failure surfaces passing through some of that pore pressure, where before the phreatic surface was well below the failure surface. And now we've got a lower factor of safety. Okay, lower, but real. This is the real factor of safety. The one that I showed at the first with a high factor of safety was unrealistic because, of course, the pore pressure, the phreatic surface was not way at the base of this thing. So it took a lot of work, a lot of effort to figure out that pore pressure regime, but it's the reality. Okay, so that is the end of our lesson today. I hope you learned something. I hope you learned especially more than one data point for pore pressure, more than one vibrating wire piezometer. And in this case, it would have been nice to have some of those dissipation tests into the basin as well, so we could extrapolate some of those lines a little bit. But more is always better than less. So remember, low pore pressure. Dissipation tests are great. Vibrating wire piezometers are great too. So we are going to leave it there. Hope you enjoyed it and stick around for the next one. All right. Thanks, guys.